Welcome back to our continuing course on fluorescence spectroscopy, principles and biomedical applications. This is going to be part 10A on fluorescence polarization assays, or I probably should have said immunoassays. I thought this would be a good time to talk about it because the previous lectures were about polarization and anisotropy, and instead of waiting till talking about sensing at a later point in time, I thought we'd do the FPIs now. Just a review from the previous section, a light beam can have a defined polarization. It's the difference between the two polarizations over the sum, and that's a valid definition. Even though this is still used in the fluorescence polarization immunoassays, they still use polarization. Just as a reminder, a better measurement is the anisotropy, because if you have a random distribution of this is for a single dipole along the z-axis. If you have a random distribution of dipoles, it would be a perfectly spherical distribution, and the way to quantify that is by measuring the intensity along each axis, which is what we have here. And we're using 2i perpendicular because there's two axes perpendicular to the z-axis. So the basic concept for all fluorescence polarization assays is simply the binding of a smaller molecule to a bigger molecule. Now, the smaller molecule is typically let's say some drug you would like to test, and in order to test it, you have to make a fluorescent analog of it to see if you have antibodies for it. So first you look at it's called just a fluorescein here, but it would really be a drug fluorescein conjugate, and the anisotropy is going to be low because the rotational rate is going to be high relative to the lifetime. But if this molecule now binds to an immunoglobulin, immunoglobulins are big, molecular weight 150 kilodaltons. Well, that slows down the rotation and the anisotropy goes high. This basic principle is what's used in all the polarization immunoassays, but there's a wide range when you look at them, and it could be very, very confusing. In fact, I was getting a little confused when I was trying to put these together. There's competitive and non-competitive immunoassays. There's sandwich immunoassays where you have two antibodies binding to the antigen. There are indirect and direct immunoassays, which I think we'll show you shortly. Homogeneous immunoassays refers to an assay that's done in three-dimensional solution. Heterogeneous would be an assay that's done on some type of surface where one of the reagents is bound to the surface. And then there's multiplexed immunoassays where you would use different colors. My initial plan, I was trying to describe these sequentially, but it just didn't turn out to be practical. At least I couldn't see that as practical for a number of reasons. One term can apply to, or multiple terms can apply to a single assay. There are different acronyms for every one of these assays. This all seemed confusing and besides the point. So we're just going to start with a schematic of each type of assay, and we'll give you an example of each type, and we're just going to call them all fluorescence polarization immunoassays, even though the classical one is for the small drug antibody interactions. So what's a direct immunoassay? That's the easiest one. Let's say you have a great big protein like a big virus, and you have an antibody against some of the surface proteins. You can, if you add the antibodies to viral suspension, you'll notice that the anisotropy goes up because rotation is slowed down. The advantage of this type of immunoassay, this would also be called not only direct, you would call it non-competitive. An advantage of this is that the target does not need to be labeled. So the thing we're looking for doesn't need to be labeled. The only thing that needs a label is the antibody against the species we're looking for. So that greatly simplifies the assay, because as you'll see later in this lecture, a simple polarization immunoassay can require a lot of chemistry. This is just another view of looking at a polarization immunoassay. In this case, you might have noticed they used FAB fragments. We'll speak about this more than once. FAB fragments are the antigen binding part of the antibodies. They're 1/3 or so or smaller of the size of the antibodies. So they will allow you to measure larger things because they have a lower polarization to start with. So here we have the black dots are the antigens, and let's say we have no antigens in the solution, or very few. So we come down here and we see most of our labeled antibodies are free in solution, rotating quickly, a low polarization. Now, if your sample has a lot of antigens in it, what happens is it binds up most of these labeled FAB fragments. And since most of these fragments are now bound up to some bigger molecule, that makes them all rotate more slowly, and you get a higher polarization. In terms of terminology, this is also called a homogeneous assay because all of the species are in solution, and it's also non-competitive because when it's competitive, we would have two different molecules fighting for the same type of antibody. What about direct versus indirect polarization immunoassays? This is sort of an easy one. Direct immunoassay is the antibody binds to the antigen, and the fluorophore is right on that antibody. So there should be some change in rotational diffusion because the molecular weight is going up by binding the antigen. Frequently, you don't have as much antibody to the true antigen you're looking at compared to what you can buy from one of the chemical companies. So this results in what are called the indirect immunoassays. We had a limited amount of antibodies. We used that, but in order to do it, anytime you label something, you lose protein. So instead of losing more of our antibody, we use it unlabeled and then use a secondary antibody, which is directed against the heavy chains, and these are widely available almost any heavy chain you choose. So we would call this an indirect immunoassay, but very convenient in terms of losing less of your primary antibody. Okay, now let's look at a competitive fluorescence polarization immunoassay. We have our antigens in green and our labeled antigen in red. So we have this mixture of labeled and unlabeled antigens, and we want to measure, we're using this to measure the amount of unlabeled antigen that is in the sample. So what might make this simpler to understand is the mixing of the reagents can be sequential or simultaneous. So don't worry about that right now. So you add antibody against your antigen to this solution. Some of the antibody binds to the labeled antigen, and that gives you a high polarization. Some of the unlabeled antibody binds to the antigen, and that displaces the labeled one, and the polarization drops. I'm going to go through this slide again because this is sort of one of the fundamental concepts, and it's very easy to get mixed up on this. I think the way this would probably be done in practice would be by a sequential addition of antigens. So what you would start with, if you did it sequentially, is you would start with your antibody solution and add some of your red or your labeled antigen to that. Give them a chance to bind together. So now you have a system poised. The labeled antigens are all stuck to the antibodies, and you get a high polarization because the rotation is slow. Now we're doing this sequentially. You add the labeled antigen, and the labeled antigen can display, I'm sorry, I got that wrong. I told you it's confusing. We add the unlabeled antigen, and that competes for the binding sites on the antibodies. So every time an unlabeled antigen binds to the antibody, it displaces the labeled one, and the displaced one rotates faster, and overall the anisotropy goes down. You might want to look at this slide a couple times to get it internalized. It's easy to mix up with antigens and antibodies against antibodies and all of those things. So let's look at how this works again and how the anisotropy drops. So first we have a solution of antibodies against some target protein. And the target proteins are going to be labeled in green. When we mix them together, we're going to get, that's the labeled version of the antibody that's binding what looks like the antibody. We get a high polarization because most of these labeled ones with the stars are bound up. Now let's go to the other situation where the solution contains some of the molecules you're interested in. So you weren't really interested in this part because you were just setting up the assay. What you're really interested in is how much of the target material is in the sample that you get from the patient. And in that case, the unlabeled antibody, which we put as the orange balls, competes with the labeled antibody, displaces some, and that results in faster rotation of your labeled tag, and the polarization goes down. I must admit, this seems to be like quite a roundabout way of doing things, but it's become a dominant method in drug discovery, is to do a competitive assay. And I always thought it must be have a smaller dynamic range, but they seem to work quite well. Here's an example of a very simple competitive polarization immunoassay. Here we have a cortisol, and we have fluorescent labeled cortisol. And the goal here is to measure how much cortisol is in the sample, not how much labeled cortisol is in the sample. So we look at the polarization versus this, like your calibration curve, versus the cortisol concentration. And as the cortisol concentration goes up, you displace more and more of the labeled cortisol from the antibodies, and that rotates faster and it goes down. So what was required to do this assay, first of all, you had to get a cortisol analog. So you had to figure out how to make that. And in this case, it was made by an amine derivative of cortisol reacted with fluorescein isothiocyanate. The assays were performed directly on serum. So this is a homogeneous assay. And the important thing is no separation steps were required to do this assay. So the change in polarization is really quite substantial compared to some of the assays we'll see in a few minutes. And the change is substantial because the unlabeled cortisol rotates very quickly. It's a very small molecule. And when it's displaced by the cortisol, the polarization drops. And we'll see this is an order of magnitude larger change in polarization that is seen for many competitive polarization immunoassays. Okay, let's look at the same type of immunoassay, but in this case, we're looking for a biomarker, creatinine kinase. This is one of the cardiac markers that are used if you get taken to the emergency room for heart attack. They'll do a panel of cardiac markers, and creatinine kinase will be one of them. And we have an immunoassay done here. The important thing here is you have to look very closely to notice this. But first off, because the marker that you're looking for, the creatinine kinase, is larger to begin with, we're going to get a smaller change in molecular weight. So when the labeled creatinine kinase binds, it already has a relatively large molecular weight and has a good amount of polarization. You bind it to the antibody. Yes, the polarization goes up, but you see it only goes up by a small amount. So these values here are at least an order of magnitude smaller than those on the previous slide. And that's because of the size of the antigen. And this is going to be a constant theme throughout this series of lectures. If you look at this table here closely, you'll notice that the change in polarization is always larger when the lifetime is longer. That's because if the lifetime is longer, it gives the creatinine kinase more time to depolarize. And then when it binds to the antibody, it's slowed down, and you see it better than you see it with a short lifetime molecule where the creatinine kinase has not had much time to rotate. So what is the effective, really what we're talking about, is what is the effective molecular weight on doing these assays, and it's really what is the effective molecular weight on the rotational correlation time. And you can calculate this for a dry protein or a hydrated protein. You'll see in a minute they're always a little larger for a hydrated protein. This would be the simple expression for relating the fundamental anisotropy to the observed anisotropy to the lifetime and the rotational correlation time. So that's the nice expression that you get if you use anisotropy. The bottom equation is the one that's just about always used, which is called the Perrin equation, and it has these weird terms because of the inaccurate description of the polarized light as not being appropriate, not like a light beam, but for a sphere. And we see also that it depends on the lifetime. And here is the theta part of the rotational correlation time. What does this mean in terms of looking at what is the effect of molecular mass on the polarization. So here we have a graph of just that. As the molecular mass goes up, the polarization goes up. This rotation is slowed down. Here we have what would be the anisotropies that you would observe for a typical small molecule like that labeled cortisol we've seen previously. You'll see a quite low polarization. A molecule like an immunoglobulin has a very high polarization, so we start here with a smaller molecule and we go all the way up here for the immunoglobulins basically at the starting fundamental anisotropy. Can't reverse slides on this program, but what I would say is I remember the creatinine kinase had a molecular weight around 50,000 or so. So if that's the case, your starting point is here and it binds to the immunoglobulin, so your end point is here. And so the change in polarization that you can see is much smaller if you're starting with a high molecular weight antigen. Excuse me. These are just some typical rotational correlation times and protein sizes. I just wanted to give you a feel of this. First of all, you'll notice that the observed times are almost always larger than the calculated time, and by observed, that means a protein in water, so it's hydrated. If you have small proteins, the lifetimes are already they're already longer than fluorescein, but when you get to something as large as serum albumin, the correlation times are way slower than the typical lifetime of 4 nanoseconds for a probe or even a rotamine, which a couple of nanoseconds. So this is why the sensitivity goes down as the molecular weight goes up. But in some way, we're lucky that these processes are in the same time scale at all, because there's nothing in nature that said that the rotational correlation times have to be comparable to that of the proteins and that of the fluorophores that we have, but they are, so that's useful. So here's the first of 2 examples of an competitive immunoassay. Let's see if I can pronounce this, valamunin. Valamunin is a veterinarian antibiotic that's used with poultry and pigs. And it's especially important in Europe because in Europe there are stronger limits on the amount of residues in edible foods. So they would not want valamunin in their food. So they developed a polarization immunoassay for this. So they developed 4 different analogs. I'm just going to call it the antibody. And one gave a larger change in polarization than the others. So they selected that to go with. So they made a fluorescent-labeled antibody, and then they did the immunoassay for it. And as the concentration of the antibody goes up, it breaks apart the complex that was preformed between the antibody and the labeled antibiotic. And another sort of crazy thing about this is, I guess things are more difficult to do in Europe because they don't like using animals in Europe as much as we do, so they were forced to do this in poultry eggs, and that gave you a different antigen, IgY rather than IgG, but they're essentially the same. So there's some chemistry right there. Now the next one is going to take a few more slides to explain, and this explains all the steps that are taken in developing a fluorescence polarization immunoassay for something. What we're looking for is the receptor interacting protein 1, RPI1, which is partially responsible for apoptosis, that's programmed cell death, and you can see it's involved with a chain of other proteins. Dysregulation of RPI1 is associated with various cancers. So this is a target for cancer treatment. They might be able to, if necessary, inhibit the activity of this protein by designing a drug that will inhibit it. So here we're starting with the RPI1, 76,000 Daltons. We're starting with an inhibitor that's going to be at a 600 molecular weight, and we want to use these species to develop an immunoassay for RPI1, which we're going to use to develop a drug against RPI1. So here's where you see what we start to get a lot of chemistry. What is first necessary in a polarization immunoassay is to get a drug analog that is labeled and binds to the drug. So you can see that can require a lot of synthetic steps, and these particular authors wound up with two different antibiotics, anti-RIP1 candidates, both of which had a fluorescein on them. So the first thing they needed to know is, okay, we know this part of the molecule bound to RPI1, but what happens when we put fluorescein on it? Maybe that inhibited the binding. Same thing for the other one. So the first step is you have to prove binding of your the molecules that you're going to use as competitors in the assay. So they looked at the fluorescence polarization of these two species in the presence of increased amounts of RPI1, and we found both of them increasing. Down here we're looking low polarization because it's just a free probe rotating in solution. Up here it's high polarization because it's that high molecular weight we just mentioned, and the same thing for the other one. So this proved that the assays were binding, would work, and you see they gave you a large change in polarization. Now the next step of this assay, you need a little bit of luck here, is these also have to be displaceable, because if they bind too tightly to the antibody, you're not going to be able to make you're not going to be able to displace any, so it's not going to work. So let's do a test on that. So another problem in drug discovery is the number of drugs that you have to form. Because when you do the statistics on this, if you take this many atoms and you ask how many different ways you can put them together, it becomes some enormous number that's comparable to the number of atoms in the universe, or if you limit things a little bit, 10 to the 23rd combinations. So you have to take some guesses and say, well, will this be inhibitor of RPI1, or will this be an inhibitor of RPI1? So a lot of chemistry there. And then you can do the assay. So you start the assay with your antibodies bound to this fluorescent inhibitor that you made, and then you add the drug that you're testing to be a better inhibitor of RPI1. And if you do find a better inhibitor of RPI1, it's going to replace some of these smaller drug analogs, and the polarization is expected to complete. For the life of me, I can't figure out why they use this alternative presentation of competition. Somehow they quantify the change in polarization as a percent competition. But you see, from this survey, they decided that actually 4 of these drugs are good candidates for being inhibitors of RPI1. And this particular drug, can't go back to the previous page, doesn't do anything. So if you were trying to work on a series of drugs, this one you would throw out. You wouldn't do any more work on it. The ones that turned out to be good competitive binding inhibitors to RPI1, you might choose for further drug development. Okay, that's the part. That's the end of 10A. I can understand that some of it is confusing. Might have to look at it more than once. I've always liked the immunology, but I frequently get confused by the terminology. So you might have seen my voice stutter a few times. But anyway, we will have some additional lectures on fluorescence polarization immunoassays.